Hello, everybody. This map is showing the Qatar, and it is located on the northeastern coast of Arabian Peninsula, and it shares the same border with Saudi Arabia. Qatar hosts FIFA World Cup 2020, and this is one of the most beautiful places in Qatar, which is called Pearl Island. I'm working at Qatar University and in Center for Advanced Material, and our research focus on multidisciplinary area that includes energy efficiency and renewable energy, perovskite solar cell and solar thermal hybrid system, and also fabricating lithium-ion batteries like anode and cathode, and insulating plastics based on polyolefins. We also work on water security to design a membrane for water reverse osmosis, and also for oil and gas infrastructure. We are fabricating epoxy nanocomposites and evaluate their corrosion performance. Also evaluate the failure cases in collaboration with industry and recommend the solution in order to not repeat such cases in the future. And also we are exploring the corrosion resistance of metal and metal alloy under harsh conditions using autoclave at high pressure and temperature. Regarding CO2 capture, we are also designing nanostructure membranes for produced water treatment in oil and gas industry. National Priority Research Program is the main funding program of Qatar Foundation. We have until now up to 14 cycles with total funds that exceed $200 million. And this numbers is the awarded budget for Qatar University. As a result, we have more than 2,000 collaboration institutions overall the world and more than 4,000 co-authored publications. So today I will be talking about tailoring Cu-hydroxyapatite catalyst for selective hydrogenolysis of biomass-derived levulinic acid to gamma-valerolactone biofuel additives. So biomass can be converted to biofuel using biorefinery. However, it takes a lot of time, million of years, to convert biomass to petroleum and natural gas. So valorization is considered an important part to fill up the depletion of modern fossil for resources. The shift from fossil resources to biomass feedstocks for chemicals should contribute to the sustainability and reduce the CO2 emission. It's predicted that 20% of transportation fuel and 25% chemicals could be produced from lignocellulosic biomass by 2030. In fact, the global dependence on the petroleum for energy is controversial. It has been anticipated that oil could fall in 2020, but it has been updated to not be before 2040. The high dependence on this non-renewable resources of energy, it raises concerns about the depletion rate. So we have to find out alternatives like conversion of biomass to biofuel. So this is the total investment for different categories. It shows that it has exceeded billions of dollars and reached to trillions for energy sector. And this could be attributed to the sustainability and eco-friendly materials that can be produced as a conversion of biomass to biofuel. Also, it is less hazardous to health, and economically it is a lower price and the high demand of the market in order to find alternatives of the non-renewable resources. In terms of performance, there's some materials that is showing the better performance than petroleum version. So biomass has become one of the most commonly used renewable sources of energy in the last 2 decades. Biomass accumulates for over 10% of global primary energy supply and is the world's fourth largest source of energy, followed by oil and coal and natural gas. Production of energy from biomass has the potential to generate lower greenhouse gas emission. So this is biomass hydrolysis include the 5 steps, which is started by pretreatment of lignocellulosic biomass by addition of dilute or concentrated acids, or even using microorganism or enzymes, which is consuming less energy and less chemicals, followed by hydrolysis of cellulose into glucose, and then isomerization of glucose to fructose, and then dehydration of hexoses like glucose and fructose to HMF, then redehydration of hydroxyl methyl furfural to levulinic acid. The composition of biomass actually depends on the feedstocks. For example, the hard wood stems has different content in comparison to soft wood stems like cellulose and hemicellulose and lignin, which is the main component for biomass conversion to biofuel. So this is the roadmap for catalytic hydrolysis of lignocellulosic biomass to bioenergy. Acid catalyzed hydrolysis is a process that generally conducted at mild temperature range from 100 to 250, leading to formation of bioenergy and furfural glucose, which can be upgraded to bioethanol to be used in oxygenated gasoline, and HMF, which can be also upgraded to ethoxylenone and different compounds that can be used in low oxygenated diesel, and oxylevulinic acid, which is can be used as platform for different conversion of different chemicals. So the pretreatment, after pretreatment, we have two routes in order to convert the biomass to levulinic acid. The first is hemicellulose, and each step, it has a certain type of catalyst and a certain condition. To hemicellulose can be converted to xylose, furfural, and furfural alcohol, then levulinic acid, and then using if we are working on cellulose, so cellulose has a different route through conversion of cellulose to glucose, then fructose and 5-HMF and levulinic acid. So levulinic acid considered to be a versatile platform chemical for a variety of market application. It can be converted to different material using a specific acid at specific conditions, and each chemical has different application. Levulinic acid is probably one of the most important platform molecules. Production of biofuel from biomass involved first fractionate the lignocellulose biomass into its main component like hemicellulose and cellulose, and then lignin. Later, the conversion of polysaccharide, hemicellulose and cellulose to a monomer like glucose, fructose, and xylose. Finally, the conversion of this monomer into levulinic acid. So levulinic acid, it contains two reactive groups like ketone carbonyl group and acidic acid carboxyl group, which display rich chemistry and can undergo a variety of chemical conversion. And also it is building block for synthesis various chemicals for application and different application like fuels, additives, and polymer, textile dyes, and antimicrobial agent, and herbicide as well. So this is a preliminary assessment by chart of the market potential of γ-valerolactone and 2-methyl tetrahydrofuran and hydroxyl methyl furfural. It's showing that this material has been widely applied and used as in biofuel application with global market exceeds $100 billion. But for GVL is the main component for decades to be used as in flavor additives with a global market exceeds $7 billion. And also this component can be used as a solvent with a global market exceeds $10 billion. So GVL is a derivative, a valuable derivative of levulinic acid, and it is the most important characteristic of an ideal sustainable liquid, which can be used for the production for both energy and carbon-based consumer. GVL has a lower melting point, -31, and a boiling point more than 200, and cup flash 96 degrees Celsius. So it can be easy stored and globally move in large quantities. So the application of GVL, it can be used as an additive to current petroleum fuels. And also it can be further hydrogenated to produce fuel additives. It also can be converted to butene through ring opening and then decarboxylation. And the resulting butene can be condensed to yield liquid hydrocarbons, fuel suitable for gasoline, diesel, and aviation kerosene as well. So there are several paths have been proposed for the formation of GVL during the hydrogenation of levulinic acid and angelica lactones. So the first route is by hydrogenation of how does it work? Okay. So the first route is by hydrogenation of levulinic acid, and then to form unstable HVA, which is hydroxyvaleric acid, and and then directly will be converted to GVL. The second route is by dehydration to angelica lactone, and then ring closing by intermolecular esterification. It will be directly converted to GVL. So in case of using, if we have levulinic esters, so it will be converted by hydrogenation to hydroxy levulinic esters. Then by ring closing reactions, in intermolecular trans esterification, it can be converted to GVL. So this is also GVL can be upgraded to a more valuable product for biodiesel applications. Through hydrogenation, it can be it can form like gasolines, compounds, and also it can be used as green solvents. So in our research, we are focused on using copper-based catalyst because it has better activity towards CO bond cleavage compared to CC bond cleavage. And also it can be used as a catalyst in liquid form for liquid phase hydrogenation of levulinic acid and its methyl ester to GVL in water and methanol. So this is our system that we are using in our lab, and in order to convert the levulinic acid to GVL. So in this case, this is showing this is the temperature controller, and here is the syringe pump where we control the feed rate of levulinic acid, and this is the reactor where we are placing the catalyst, and this is the ice bath to condense the catalyst, to condense the product, which will be collected for further analysis, like HPLC, to know to evaluate and explore the byproducts. And at the beginning, we are purging hydrogen for 1 hour to activate the catalyst at 300 degrees Celsius. So we explore different support like mesoporous silica and hydroxyapatite using copper as a catalyst. And we also explore and characterize their own morphology and using TEM and XRD, TBR, and TBD. So this is the TEM is showing the formation of copper nanoparticles in range of 20 to 30 nanometer. And this is the XRD of the copper oxide that has been constructed on the hydroxyapatite. So we explore the effect of loading of copper on levulinic acid hydrogenation, and it was found that 5 weight percent is the optimum weight percent that can lead to the high selectivity, which reaches to 90% and conversion of 60% of levulinic acid to GVL. We also explore the effect of the temperature, and 265 is the optimum temperature for high selectivity and high conversion. However, it can further increase the temperature, more byproduct can be produced like valeric acid and γ-valerolactone, and which decreases selectivity. So time on stream, just to explore the stability of the catalyst over the time as a function of conversion and selectivity. It's showing that it has been gradually reduced after approximately 5 hours. And this could be attributed to the formation of cook on the active site, which block this active site to transform the levulinic acid to GVL. So also we explore the different support like mesoporous silica, and this TEM image of the copper supported on mesoporous silica, and this diffraction pattern showing high crystallinity. And there's two routes or two paths, and both have two different byproducts. For the first path, it can form hydroxybentanoic acid, and for the second path, it can form γ-valerolactone, and both can lead to formation of GVL. We also explore the effect of different parameters like surface area and the particle size of copper, and we find out that by increasing the surface area and decreasing the particle size, higher selectivity and also higher conversion can be obtained. So also we explore the levulinic acid feed flow, and it was found that 0.5 is the optimum condition for feeding flow for levulinic acid with higher conversion and selectivity. So we also explore the levulinic acid concentration, and 10 weight percentage is showing the highest and conversion and the selectivity, and for stability using silica, mesoporous silica is showing the better performance than hydroxyapatite due to the higher surface area of mesoporous silica that reach to 1,000 meters square per gram. So overall, the potential commercial application of the levulinic acid hydrogenation to GVL process can be possible by developing non-noble metal catalysts for improved process economy. The copper nanoparticle dispersed on the hydroxyapatite and mesoporous silica support provide a high surface area and facilitating the interaction between the reactant and the catalyst, and this improved accessibility promote efficient catalytic activity and conversion of levulinic acid into GVL. The interaction between the copper nanoparticle and the hydroxyapatite also influence the selectivity of the reaction. The catalyst composition and morphology can be tailored to optimize the selectivity of GVL and to minimize the undesired side products. This selectivity control is crucial for maximizing the overall efficiency and yield of GVL production. We also, our future studies that we are trying to explore the effect of particle size like spherical mesoporous silica with different size that range from 10 nanometer to 50 nanometer. And we also managed to fabricate mesoporous silica with pentagon shape using different surfactant with very small particle size that can range between 10 nanometer. This is one of our future study. At the end, I would like to thank you for your kind attention. Thank you.